All right. This talk is on machine learning, using machine learning for GitLab issue triaging. My name is Stan Hu. I want to start off with the problem. We've got a lot of issues in GitLab, especially the GitLab org, GitLab project, which gets probably about 50 issues a day from various team members, but a number of them are not labeled with any particular group. And a lot of those are from the community. And oftentimes I'll notice that they go unanswered unless someone from the quality team or somebody in the team just goes in and tags the label manually. And sometimes people who are subscribed to those labels then go and reply to them. So the question is, can we automatically classify some of these issues with something with machine learning? Because hopefully we can train something that can recognize certain words or patterns and then just automatically classify, give it a label like adoption or code review or whatever. So that's a pretty straightforward problem. We've seen that from the beginning of GitLab needing this. This is sort of the result of all this, and I'll go into exactly how this works, but there's a channel now in Slack called Feed TanukiStan, which runs every day, and it will look at unlabeled issues or labels with no group label in particular, and then tag it with its best guess, assuming that it's confident enough. There's a certain threshold. You'll see the probability in these things. It's pretty confident sometimes. So, and sometimes it's pretty confident and wrong. But that's it. That's all part of machine learning and training data and all that. So overview, this is a lot of stuff. There's a links to the actual classifier and the project. I chose TensorFlow mostly out of naivete. I didn't really know. I know there's a lot of other frameworks out there, and I talked to Mon, who's on the customer success side. She said, "Oh, I wouldn't have started with TensorFlow, but here we go." But I also looked at what we had done before, and somebody on the security team had already done the CI abuse detector, and she had already used TensorFlow. So I thought, well, I understand that part. Let's just go and continue to use TensorFlow. So there's lots of other tools out there. I liked it because you could use Google Colab, which is sort of their Jupyter notebook / integration with Google Cloud. So you didn't have to spin up machines. You could just hit play and it would actually run a lot of your script in like a GPU environment. So that's really nice. And there's a lot of great tutorials out there. I encourage you to take a look at the Coursera courses. Google does a good job of putting interactive videos and showing you the basics from the simple hello world to more complex things. So I think it's a pretty good framework, but there may be other people who disagree. It uses behind the scenes, it uses a long short-term memory model, LSTM, and there's a lot of math that goes into it, and I encourage you to look at the link and what that means. But you probably want to start with the beginning models before you go into this, because this is sort of solving problems, with the more naive models, and it's always good to kind of start with the basics first. I've gotten this triager to actually train with GitLab CI now, because I was actually really surprised when I was doing this machine learning work that something as basic as something like this, which is just trying to classify text, absolutely needs GPUs. Like if you try to running on your local Linux machine without a GPU, it will just take days and days and days. With the GPU, a normal training epic can take 5 to 10 minutes or less, but with your own computer, it might take a couple hours. So there's a magnitude difference there, maybe 5 to 10 difference there. And it runs nightly on a CI schedule. So there's a CI schedule that just runs it every night at 2 a.m. my time, 9 p.m. UTC. So this is a crash course in case you haven't done any machine learning. I hadn't done that much. I'd read about it, but this is sort of the prototypical model you people see. And there's a couple different layers here. The input layer is like your input. So it could be, let's say we were trying to build a spam detector. Your input layer would be the words in your spam text, and then the hidden layers are things that help you get to the output layer. The output layer in this case is just the one point here, but that could be example like a spam detector. Give me as 1 if it's spam and 0 if it's not. That's a classic example. And the hidden layers are in there to kind of allow you to use different weights and have more and more complex models. But basically, that's sort of the breakdown of every neural net you'll see. Drilling into the actual neurons themselves, every neuron has inputs. So and they're denoted. The W is denoted by the weight. The weight is denoted by W, and then X is the actual input value. And so you just basically multiply the weights by this input value, and then they all feed into this the circle here is a function activation function. So you can have many different activation functions. On the right is a number of them. You know, the one that is used for this issue treasure is a sigmoid one, and you can see that it's, you know, it outputs something from 0 to 1, but like it's not a linear relationship in any of these. So that's one key feature of that neural nets. You're trying to solve a complex problem. It's not, you know, unless you're trying to solve like a linear equation, most of the time in things in the real world are nonlinear. So these activation functions sort of reflect that. And you know, there's all sorts of talks about why one is better for another depending on your use case, but in this case, I'm just going with the sigmoid. Any questions so far? Another thing you'll hear a lot about is, well, how does this neural net actually get trained? But it really comes down to this core concept of gradient descent. And if any of you have taken calculus, the idea is that you try to follow sort of the path where the where the second derivative is pointing you to. So if you do a lot of math, you can figure out like which direction in the x and y axis will get you towards your goal. And you know, you don't actually have to implement this anymore because all these frameworks already do this for you, but it's good to be aware that this is how the magic works. It really just comes down to math. You put enough inputs, you know, try to adjust the weights based on how fast this little graph here shows you like, well, I'm going to try to move in this direction on the W axis from left to right. That's your learning rate. And so you may take a little step and then you may reevaluate your model and then just see how good it becomes over time. And that's sort of the training process. So that's just a high level of it, how things work. Probably just to give you a flavor, but there's a lot of math that goes on beyond. I'm not going to get into the calculus behind all this. So at a high level, TanukiStan is pretty simple. You know, we got to get the training data in there. And the way I do it right now is export the issue CSV. And then you take that CSV, you actually translate, you tokenize it, and you translate it into numbers essentially. And then you plug these numbers into the model. And then once you've trained it enough, you save it out to a file. And there you go. The actual CSV import, you know, the first thing you always need is a data set. And, you know, when you start with machine learning, they'll often give you the data set. But oftentimes the hardest part is actually getting the data in the first place. And in this case, we have the export project functionality, but I didn't want the entire project, just wanted the issues. And so right now we do have an export CSV button that allows you to export issues. And I first started with that, but it only allows you to get, I think, the first 15 megabytes, and I wanted all of it. I wanted every issue that GitLab ever saw. So I actually had to just do some hacky stuff on the console that just allowed to bypass the restriction and save me a file. And there's an issue there to actually make that like a normal feature. We just click a button, you can generate you know, the zip file completely, and then you don't have to worry about getting it emailed to you and all that. I store this in LFS right now, and it's zipped. It's said zipped with a password, and it's because of confidential issues. I didn't want to leak confidential issues to people who happen to be perusing this repository. So the next step is to tokenize all this stuff. And so, you know, it's a very simple concept. You know, you're just taking these words and trying to turn it into a number, right? Because machine learning, that's how it works. You think of it as a giant matrix multiplication optimization problem. It doesn't really work on text. You've got to translate into some meaningful representation. In this case, words can be mapped to numbers. And there's a lot of tools for this already. TensorFlow includes its own tokenizers, and this is a pretty simple example. You know, if you substitute the word hello for 3, you can see that, you know, all the hello. Oh, I'm sorry, is that right? Yes, 3 is hello, and 4 is how, and 5 is R, and 2. And you can see that that just becomes an array of numbers, right? Pretty straightforward. And if you plug this into doing labels, and the group labels in particular, I've just filtered out all these scope labels. So you see the mapping here. And these are the existing labels that we're seeing. So I did have to do some text changing because like the tokenizer will assume that spaces means like a different word, and so it automatically will do that. I didn't want to split up project management, for example. I really wanted to consider as a whole as project management. And for issue, you know, we got to tokenize 2 things: issues and labels. The labels are very straightforward. You can see that there's a clear mapping of the 46 here of 46 labels. Issues, there's a lot more stuff in it, like punctuation, words that actually don't contribute that much meaning to your so like stop words are called, like to, is, are. Grammatically they're important, but from the machine learning perspective, it just adds more complexity and doesn't, and often gives you worse results. And then for issues, I just simply tagged on the title and the description together to make the whole issue text. So this is an example, like this is like a issue for, I think, a geo backup thing. And so you can see that when I tokenize it, it strips out a lot of stuff, makes everything lowercase. So, so that's kind of what the machine learning model sees. It sees at least this kind of sanitized text here. And then if you actually translate to numbers, it'll look like something like this. You can see at the end, it's padded with zeros because the text doesn't go beyond a certain length here. And then when you train, there's always this talk of having different sets of training data. So you start out, I've got this giant CSV, I've got to split it somehow, right? I got to split it to my training set and then a validation set. Basically, the validation set's idea is like, well, I want to see, based on if I trained against this set, I want to see how good these predictions actually come out to be in this validation set. So because the CSV, so we've got, I should back up. We've got unlabeled issues and labeled issues, right? So, but by far the majority of them actually have been labeled. So that's my training set, right? So I know that some human tagged it and said this belongs to the compliance group, or this belongs to search, global search, and so forth. But then there's other, so when I started running this thing, I started tagging issues with automation ML because I wanted to be able to know that, hey, I don't want to have this self-reinforcing algorithm, which is I've tagged this issue, I know it's this group, and it's always going to train against, stuff that it's already like, it's just like a circular logic, right? I've labeled as global search, therefore it's going to be global search going forward. And so I'm basically filtering out those issues that I've tagged with automation ML because I don't want to pollute. But if you notice the message, I say, well, if you're going to help me, tag this issue with automation ML wrong, because I know that means a human came along and said, hey, you were wrong about this prediction. Here's the right one. So that's the idea here, is that this can be a form of learning over time. Does that make sense? All right, so now let's actually get to the text classification. So in the earlier slides, I showed a kind of a simple neural network with one point as an output layer, one neuron as an output layer. We're trying to actually classify, what is the probability that, this issue belongs to the specific group. So the output layer will actually be the number of groups, right? So in this case, I think there are 47 groups. So the output layer will actually have 47, and the Y outputs for each of them will be the probability that the neural net thinks that it belongs in this group. And so if you actually look at the model I use in TensorFlow, it's using a bunch of things called embedded layers, and then it uses this LSTM model. And the idea is that it has some memory. So if I said something in the beginning of my issue, and then I said something in the end, it can kind of it can kind of correlate and remember that I said something that might be important from the beginning. So it remains to be seen whether this is the best model. You could have done a word frequency, but I just wanted to do something that was, that I thought was, that could work, and that's kind of what I went with. And the output, and and at the end of the second, there's two dense layers. The last one is the actual output layer here, and you'll see that in the actual code here. There's just a couple things to point out here. The label count, the last dense layer is the label count +1, and the reason why it's +1 is because if you look at the tokenizing in the beginning, actually it starts out as 1, right? So it's not actually starting out at 0. So that actually threw me for a while because my results were all were not understandable, and it turns out +1 is really important there. Not going to go too much into the model. You'll see this model example in a lot of other textbooks with text recognition and classification. So it's nothing super. Yeah, there's a lot of ways to model something, but I just kind of maybe my first, third or fourth iteration just to get it going. Anything else to point out here? There's this loss function. Basically, the whole training is operating on trying to reduce the amount of cross entropy loss, which is basically a calculation of just it's a difference in the calculation of the two probability distributions. So the idea is that like I can figure out whether I'm actually getting better at getting closer to my training data, right? And so that's how it's optimizing for, tuning the weights and things like that. So, but a lot of that magic is happening behind the scenes. You don't actually have to know these days about the details of the math. The nitty gritty stuff is sort of taken care of. You just have to worry about the high level, the data, the model, and things like that. And I actually got this running in GitLab CI. This job may be confidential because of the whole confidential issue thing. And this, I have to transfer this project to probably a more public project, but you can see that it's training 100 epochs based on that variable over here. And it'll show you the loss, the loss, the lower the loss, the better, right? And the accuracy is basically, the accuracy after it, every epoch it's doing, it's kind of coming up with a bunch of weights and trying to see like, okay, based on your data, how accurate are you getting? 100%, one being the most accurate, 0 being no accurate. So the idea is hopefully you see improvements right away. You can see that we jump in these graphs. This might be an old graph, but it's the same idea holds. As on the left, we've got the red line is showing your accuracy on your training set. So you hopefully get better and better, right, over time. And then you take you take, like, let's say we took 20% of the data as your validation set, and you say, okay, well, based on that, how good am I really improving? Because it's very easy to get to the point where you're just optimizing the heck out of your own training data, so you get 100%. It's like, hey, I've got this result, but I'm just constantly just optimizing for my training set, but it doesn't actually reflect real world performance. And that's the whole point of the validation accuracy. And you can see in this graph, it sort of pegs out at 60-70% accuracy. And part of that has to do with that there's a lot of ambiguity in the data. Part of it maybe the model isn't ideal. But the idea is that you can easily get to the, if you want to see these kind of graphs, you don't want to see it like going all over the place. And when I first was starting it, I was seeing these crazy graphs where we're going up and down, and that kind of tells you that something is wrong with your model. And on the right is just the plot of the loss function. So hopefully training goes up, loss goes down, and that's kind of the general trend you're seeing. If you see the validation loss sort of holding steady, basically this red line is constantly going up, it basically tells me that you're training, you're almost overtraining at that point, because you're just optimizing for your training set, and you're really not getting better real world performance, right? So there's this balance in machine learning, is like trying to balance, like, not overtraining but not overfitting your data to the real world. And then there's some mechanics of just actually saving the state. It's actually pretty simple. It's the tokenizer stuff you saw earlier. It's just JSON files. So you just save them out as files, and then the TensorFlow in this H5 format, you just say, hey, save it to this binary format, and essentially you've got this serialized model ready to go. Now on the reverse side, it's making predictions is actually pretty easy. You just load those models. You load that JSON file, you load that binary file, you get your issue text, you tokenize it, and then you make the prediction. And the prediction part is actually much cheaper than the training part, surprisingly. Not surprisingly, I guess. So, this is the actual prediction function here. So you can see that we tokenize it, we turn the text into numbers, we pad it out a bit to make sure everything is sort of normalized, and then we'd run the prediction. And I just want to point out this red area is actually where this the mapping from these probabilities to the actual group. So this NP argmax is basically say, hey, find me the highest probability in this prediction, right? So like I had the output layer, as we saw before, was 46. Let me go back here. We've got 46 different outputs, and one of them is going to have the highest probability. So I'm going to choose the one with the highest probability because that's my best guess where this issue belonged to. And then basically the second, there's also this confidence level that this prediction model returns as well. As I said earlier, we've got to change the label, had an underscore in it. It's just mapping it back. And then that's basically, I've got a guess, I've got a prediction. And you'll see these messages now in the GitLab issues, and it'll tell you that, hey, this was an issue talking about not being able to create forks. And probably because it mentioned fork a lot. You know, the triage, the machine learning model said source code usually belongs to fork. So I'm pretty confident here that it's a probability of 1. And you'll see here this automation ML wrong is basically my way of nodding people to kind of like help improve the data over time. I would say the predictions don't always go right. Like this one happened 3 days ago, and yeah, it was amusing to see this conversation with someone in the security team. And well, you know, it's not always up to date because I think we've been shuffling labels over time, and so there's that part. This training data might have, this training data might have been extracted a month ago, and so we're already out of date, right? And so that kind of lends me to my next final point about like what's the future work. Well, we don't really have this incremental learning model right now. Right now, I've got to basically export the giant CSV and then just rerun the whole training, which takes a couple hours. I've got to manually generate the CSV in the first place, so all that stuff is a little bit manual, but kind of a pain. And as you saw earlier, the tokenization is actually really important. If you don't clean up a lot of that noise, you get a lot of noise in your output too, right? So there are things in our issues that we mentioned users, like I don't filter that out. So sometimes there may be a correlation for specific team members, right? I think like let's say Dylan is mentioned a lot in search. It may start to just train off Dylan being part of search, right? So things like that, it's not really, either we filter it out or we just, we actually let it do that. I don't know. I mean, you could argue one way or the other. Code references, we mention code all the time, but like I said, it doesn't really have any knowledge of like, what does it mean to be a Ruby method and things like that. So anyway, things like that can really improve your training outcomes. The model I show is pretty complex model. It takes a while to train, but there may be more simple ones that are just better and less energy intensive. And then the classification doesn't even pay attention to the label. So a lot of time team members have already labeled it like this has to do with Elasticsearch or something, and like that is just a giveaway. And this is not I was trying not to like cheat, but like that's something you could use to say, hey, this has to do with this particular topic. It probably belongs to this group too. And then lastly, just automate this within GitLab for everybody, because I think the dream is to make this part of the GitLab, and just every project should be able to have an engine which helps triage issues in a way. And so that's a whole different challenge, because like I said, this is very specific to GitLab, but there may be ways people use GitLab issues and labels very differently than we do today. So that's my quick 22-minute rundown. Is there any questions that I can help answer here?
Yeah, I have a question, Stan. So long-time listener, first-time caller. Thank you for putting this together. This is excellent. The question I had was, you mentioned that you exported all the issues into CSV. And I'm just curious, why export it out, and why not do like a database level something? Just curious.
Yeah, I mean, we could do that. That's another way of automating it. And I think we do some of that ELT right now for some of our other data warehousing work. So certainly that could be done. It could be done even by webhooks too. Like if we got every new issue that were triggered, we could store it internally too. So there's many ways of kind of doing that. I just did this because it was the easiest way to get the data right now, right away in a format that was easy to work with, because things like, tag and issues have a bunch of labels, right? And so you have to make sure that you get all that data too with the labels and associations with it. So the CSV is really nice that it tells you, X, Y, and Z are the labels, and that's it. So it's a very easy file format to work with, and I could get it within 20 minutes or so. But you're right. I think some ELT thing or some way of having this data accessible to everyone would be nice.
And what are your thoughts in terms of adding comments on the issue as part of the training data? Because like you mentioned, somebody may have gone in and commented about where something belongs, so that might be valuable. Yeah, I understand why that wasn't done in this run, but I'm curious, like, are you?
Yeah, absolutely. I thought about that too. I think part of the challenge is sometimes you get a lot of noise in the comments too. So like the bot chimes in a lot too. So you've got to filter that out sometimes, or, but certainly like if it's actually like if we start to train it, like what's a human response and be able to use that as like more information. I kind of want to just, yeah, I mean, so absolutely more information probably will help models, but I didn't want to overwhelm the first attempt and just throw. And it was also interesting to see like how good, because I first just started with the issue description. How good can your model be with just the issue description? And it turns out it actually was pretty good. And so the question is like, how much more information do you need to feed this thing before, you know, it gets unwieldy or useful, right? So there's a balance with machine learning too. But certainly, like if we were cared about 99.999% accuracy, hopefully we'd be able to understand everything that happened in that issue, and the machine learning model would always be right because it took everything into context.
Thank you.
Did you have some comparisons to other models that you'd have tested before? Sorry, I realized I just spoke over somebody, but like the total accuracy in the end, did you try a bunch of different models?
Yeah, I tried a bunch of models. I didn't actually do kind of a thorough investigation because mostly I was just trying to get results that looked pretty accurate to me. Like I didn't want to, that was sort of my my goal here. But I think I first started out with just doing issue descriptions. I think I didn't even bother with the LCM model. I think it was a much, I'm trying to remember, I have to go back in the history, but it was a much simpler model and I could train it on my laptop and it still worked reasonably well. So I think, but then I think then it's like, oh, let's throw in the issue text and like and just see like, does it actually yield better? So it would be interesting to kind of do, you know, comparisons that way. But the thing with machine learning stuff is that the training can take a couple hours, and so you kind of have to juggle it. And the tooling is kind of difficult right now, even with GitLab, right? There's a lot of tools that are trying to figure out this MLOps space and how to manage your data and your models well, and that's kind of goes into like what can GitLab do better to facilitate those kind of comparisons, right? Because ideally is as you say, just I want to throw this model A, model B, and have like GitLab do a bake off and tell me like all the data that you came out with and just have that comparison so that, you know, it's not so manual right now.
And so you mentioned it taking a couple of hours for training. Is that how long it takes in CI at the moment?
Yes. So when I first started, I used Google Colab, which is basically they basically have a Jupyter notebook that plugs into their VM. So you hit play and it basically will run it on their VM and do your training. And so I think that was a little faster because they offer a much more powerful instance to you. And then, but I really wanted to get on GitLab CI and just use like the basic, I think N1 standard like one with, you know, enough memory. And so the GPU may not be as fast as the ones that like Google has. So I think it took 3 or 4 hours at least on GitLab CI, but I haven't tried with the more expensive machines because if you've looked at the pricing, these GPU enabled VMs are very expensive. You could spend thousands of dollars a month with a single instance. So I was trying to avoid that.
How would this be extended to like other attributes? So you apply group labels to it. Would it have to be a whole new model if we wanted to do something like type labels internally, or could you just kind of repurpose the existing model based on what you see?
Yeah, that's a good question. I mean, I think you could actually take into account, like you could just extend it by saying, hey, these are all the labels I care about, and then maybe see whether in the classification you actually see the probability that this label actually belongs with this issue. You could do something like that where, you know, the model could be revised so that you actually care about like 90% predict like that this label actually belongs with this issue, and kind of a more general approach. So, you know, certainly it could be done that way. I don't know how, you know, whether, and there may be other ways of doing it, right? There are a lot of ways to do machine learning, and that, so you could, I could see that being kind of the first iteration to try and just see like, hey, if I threw all the labels at it, does it get confused, or can it actually kind of figure out like this actually belongs with this issue? This is kind of a, yeah. So that's a kind of a different problem too, because it's a multi-label classification. This is kind of a single label classification. So you're kind of pitting every group or every label against each other. So there's that. So, but yeah, I definitely think it'd be extended in different ways.
Stan, you mentioned going through a few iterations with different models. I'm just curious which other models you tried.
Yeah, it feels like a months ago. I think I'm trying to remember now.
Were they all neural networks, or did
They're
you
all neural
try?
networks, right? It's just that
Yep.
I didn't start with an LSTM model. I think I first started with doing the spam classification problem because that was really annoying me, because every weekend that GitLab tracker would get hundreds of spam. And so I was just trying to against that. And I was just trying to do a simple, like, just, I think it could have been something related to word frequency even. I got to go back in my notes, but it's been a while since I looked at that. But I remember it just, I think it was, if you look at some of the, beginning training with machine learning, there's a lot of spam stuff. And so I think I used more of those models that were much more straightforward and didn't require GPUs to actually finish training.
Yeah, I ask because there's this well-known issue in data science where a lot of times you get very good performance out of the simpler models. And so a lot of production models are actually just logistic regression rather than neural network.
Right.
Don't take so long to train. But yeah, that all depends on the problem you're trying to solve, I guess.
Yeah, and I will say, I think I was very surprised to see the CI abuse model being just dead simple. It was really just like two layers almost, and just a few neurons, and that was it. And they just trained against that data. And I think same with the actual spam detector that we have going in production soon. It's actually a really dead simple model too. So, you can get great results for that.
Stan, I've got one more question with regards to the process of what you've built here. This presumably lives in a different repository, a different project, correct?
Correct.
And then the model itself, where do you keep that? Is that also within that project, or are you?
Yeah, so I most of it's in a Jupyter. It's in a Jupyter notebook basically, and in the CI, you can actually see it in the CI. Let me, if I can bring up my browser here. You can, this is an example of the Jupyter notebook in Colab right now. But the model itself is somewhere down here. There's a plot. It's the model is basically in here, and the CI job actually just converts the notebook to a Python script and just runs it. So I don't know if you worked with Jupyter Notebook, but it's really a nice way to kind of just play with data science and try out different things.
Yeah, yeah, and this is interesting to me because I work in sales. I'm a solutions architect, and a lot of customers ask me about this kind of stuff. Unfortunately, they look at how GitHub is doing what they're doing with Jupyter Notebooks, and then they go, well, do you have something equivalent? Because that's what I want. And not really realizing what it is that they really want, right? Which is basically just a way to store Jupyter Notebook and operate on it. So, which we do. So this is interesting because now there's a real life example that I can show them and say, yes, this is possible. This is not outside of the realm of what GitLab can do. And I know it sounds kind of silly and dumb question, but you'd be surprised how many customers ask such silly questions.
Sure. A lot of people want to cover their bases, right? They want to say, we're doing machine learning. We want something that supports machine learning, right?
Yeah, and to that point, I think the announcement that we made about supporting GPUs was huge. That's starting to draw attention, and people are starting to see that we are in the right path in terms of getting there. So the natural question is, oh, wow, so now I have, this kind of use case, where can GitLab help us? And I think this example that you have is a brilliant example because it's showing people that we take our own data and we're dogfooding and we're actually being able to produce results that are valuable and valid. But I think the mechanics of how we're doing it right now, I think is still MVC. Like you mentioned, a lot of manual stuff. So once that starts getting automated, I think there are a lot of good interest stuff. Very interesting.
Right, and so we have an ML ops team that's we're forming right now. We're still hiring for that. So if you know anybody, feel free to point them to Bartek. You know, right now my focus has been like just getting like those GPUs on the runners, because I realized that, hey, I can't even train at my runner. And then I realized that customers were asking for this too, and we just never prioritized it because we had a lot of other things to do, right? And so we got that running, I got this running, and then the second question I had was like, well, how good is our Jupyter notebook support right now? Because that's by far how the majority of way people use machine learning data science right now, just in their Jupyter notebooks. So, you know, things like that, like I've just been fixing a few bugs, like our images are not showing if you use a markdown table, right? Things that's simple. So I'm trying to tackle those because that's kind of low hanging fruit. It's sort of to me, it's like just basic requirements for anybody doing any kind of data science with GitLab, right? And so we can talk about all the fancy stuff, and that's kind of the ML ops team is going to be focused on, well, how do we improve the workflows? How do we make, you know, experimentation a lot easier with these things and all that? And there's a lot of other tools out there. Nobody's solved this yet. Every tool I've seen out there is still trying to figure it out. They have their opinionated way, but like it's a learning curve. Like there's Kubeflow, which I've read the documentation for it. It's like, it's kind of a lot of like, here's how you're going to do machine learning with Kubernetes. And it's just like, they throw Kubernetes at you, then they throw all this other stuff at you. And it seems really powerful, but you probably take a week to kind of figure out, you know, how to even get started. So I think our goal is kind of make it easier. And I think Google's done a good job with Colab. They made it, you know, easy for you to just put play and it runs on a GPU. And so we need to be thinking along those lines too, because, you know, at the end of the day, that's kind of the basic tinkering that people are going to be doing.
In terms of using TensorFlow, there are so many tools like that out there. What drove you to choose that?
Yeah, I mean, I think it was just naivety. I heard a lot about it. I saw that we had been using it internally for our CI abuse. I think I talked to Mon, who's on the customer success side. She said I would have started something with like Scikit or something like that, and you know, PyTorch. So those are all great to start with. I think Google's done a good job of putting out online videos that make it basically handhold you through the way of like actually using TensorFlow. So in terms of like the learning curve for me, it was just really an open learning, like it's just a good experience, right? Because the Coursera stuff is very interactive in terms of like, here's what we're going to do. Now you write the code for it. Now we're going to verify your actual solution. And so for me, you know, I learned by doing, and I really enjoyed that, right? I enjoyed the process of like actually not just learning from textbook, actually getting, you know, my thing saying not correct and, you know, try again kind of thing. So, but I'm sure there are other frameworks out there have equally good materials out there. It's just I picked one and just ran with it. And I think also I was thinking, well, we might want to run this in a Go microservice, and I noticed that TensorFlow had more support for doing that kind of stuff. So I'm like, that seems much more attractive. So there were kind of a multiple reasons that I was kind of just doing this in the back of my head. Well, great. If there are no other questions, I think Mark and I might have a working session and trying to get his environment up. You're all welcome to join or leave, but thanks everyone for your time.
Thank you, Stan.